Hi everyone, welcome back to 102 CDE. We're on topic 5, and this is said, as it says here, it's extended topic 5. And this is about superposition theorem and nodal analysis. So if you're 102 CDE, you will need to know all of this. If you're 102 CEM, you will only need to know the superposition part and the thevenin and norton equivalent circuits part. You will not need to do the nodal part. Okay. Any queries, just send me an email. Okay, so here's what we're going to do. So this is from chapter 4. So we've got superposition theorem. So we're going to look at that with independent sources, both voltage and current, and dependent sources to see what happens when we have dependent sources in there. We're going to do about thevenin equivalent and norton equivalent circuits. So a thevenin equivalent circuit is where you reduce everything down to one voltage supply and one resistor, and a norton equivalent circuit is where you reduce everything down to one current source and one resistor. And also you can convert between the two using the current divide, the source conversion rule, that we discussed in previous sessions. And the nodal analysis part here at the end is the bit that the 102 CEM students don't need to do, but the 102 CD students do. Okay, so let's crack on with it. So here's a circuit. So look at the circuit here on the right. And say we want to find what the current is through R1. Okay, in this case, the solution is relatively simple because we know from our topic 4 material where we're adding and subtracting power supplies and things like that, that you could add the 12 volt and the 6 volt supply because they're both pointing in the same direction. So 12 plus 6 is equal to 18. And then you've got one power supply, one resistor. You can use good old Ohm's law. So V over R is equal to I. So we can do the calculation here. So we have 18 volts divided by 6 ohms, which gives us 3 amps. Okay, it's that easy. Let's move on to a slightly more complicated example. So let's take a look at this circuit now. So like with what we were talking about when we did mesh analysis, you can't actually have this analyzed using your basic circuit analysis techniques because you've got a supply here and a supply here. They're pointing in opposite directions and you've got the components in between them, so you can't combine them together. So you can't actually use the analysis techniques from topics 1 and 2 to solve this one. Okay? So in this situation, you could use nodal analysis like we're going to come to later on. You could use mesh analysis that we already did in topic 3, or you could use it using superposition theorem. So superposition theorem is where you look at the individual contribution made by each of the sources. So if I go back to this slide here, then what I want to do is I want to find the contribution made by V1 and find out what the current through R1 is for just V1, and then do the same thing again. So put V2 back and find the contribution just by that by removing V1. And then, like the name suggests, superposition theorem, it's like when you've got two waves, they can superimpose on each other to make bigger or smaller waves. You can just add the two combinations together to then give you the final answer. So let's do it now with this basic circuit example. So here's our 12 volt source. We've taken out the V2 source and we've replaced a voltage supply with a short circuit. So you can see here, I've got a short circuit there. If it was a current source, you would take an open circuit. So if you replace a voltage source, you replace it with a short circuit. If you replace a current source, you replace it with an open circuit. Okay, so again, we've removed V2, we've just got V1, so therefore we've got 12 volts over 6 ohms, which gives us 2 amps. Okay, so now let's find the contribution made by V2. So here we've short-circuited V1, replaced V2, so now we have a 6 volt supply, 6 ohm resistor, so 6 over 6, as shown here, gives us 1 amp. And that 1 amp gives us that solution. So now we have the 2 amps from here, the 1 amp from here, so when we add those together, they're both going in the same direction, so that's 3 amps. Okay, so it's just the contribution made by V1, say I1, and the contribution made by V2, say I2. Add those together gives us 3 amps. If I go back to that slide there, you can see here that you've got 3 amps, so it works. Okay, I understand that that's a relatively simple example, but the principle is exactly the same. So no matter what happens, no matter how complicated the circuit is, this method still works. Okay? So let's go back to that more complicated example that I mentioned earlier. After we just say what the quotient is. So this says that the basic principle of superposition theorem is that we consider the effects of each source by removing all of the sources and then add the separate contributions together. Here, note this bit here, it says superposition works because apart from the current for supplies, all the components that we're considering here are linear in operation. So if you double the current through a component, the voltage also across it doubles. Okay, and this is common for resistors, which is the only component we've met so far. In topic 6, in the next video, we'll be looking at capacitors and inductors. But we'll also find that there is the same thing for those as well. So there's the statement. I basically said that before, so I'm not going to read through that again. So here's our complicated example. So let's apply superposition theorem to this circuit here. Okay, so here we've kept our V1, we've removed our V2, and now what we want to do is we want to combine these resistors together to find out what the total resistance is. And now, because we've only got one supply, we can use the analysis techniques from topics 1 and 2. So that's very good. So we can still use those. Okay, so first thing is to combine all these together. So in this blue circle here, you've got the R5 in parallel with R3. And as I said here, basically when you combine those together, it's 5 ohms, because in this case they're both 10 ohms, and when you have two identical components in parallel, the value halves. Okay, whoops, wrong way. So then we consider the next one. So then that our equivalent, which is for R5 and the R3, our equivalent one, say, that would then be in series with R2. So you'd have 5 plus 5, which would give you 10. This combination here, which I'll call R equivalent 2, would then be in parallel with R4. So I would have a 10 in parallel with 10 again. So this R equivalent 3, which is represented by this green area here, is equal to 5 ohms. And then I add this R equivalent 3 to my R1 to give me my final resistance, which is 15 ohms in total. So now I have the total resistance of that. I can then find the current from the supply. So I've called it IS1, current from source 1, or you could call it I1, whatever you wanted it to be. And if we want to find the current through, or in this case, so we can't call it I1 because the answer is I1. So we want to call it IS1. So the current is going to come from the source, it's going to go around, and then it's going to split at this node there, where R1, R2, and R4 meet. Now remember the rules that we said for current divider, you put the other branch on the top. So the other branch in this situation would be the combination of R2, R3, and R5, which would be this situation here, which would be what I've called R equivalent 2. So you put the R equivalent 2 on the top, you put the R equivalent 2 plus R4 on the bottom, multiply by the current, which is 0.8, and that gives us 0.4 amps. So now we found the contribution made by V1. Okay, so now we can put V2 back, short circuit V1, and we end up with this circuit here. Okay, we do exactly the same process, so we would find the total resistance of this circuit here, find the current supplied by the source, and then use current division to find that again. Just note here that the current is pointing downwards this time, it's not pointing upwards like it was here. There V1 is pointing up, here V2 is pointing down, So the current would come out of this terminal here. It would go around here. It would have a current division here at this node here. So then you would have to find the current going through here, and then you'd have to do current division again here. So in this particular case, you would have to use current division twice. Okay, so I'll let you have a go of that yourself. So then you have I2 in this situation, which is equal to 0.1 by current division. So you had I1 pointing down, you have I2 pointing up, so the two are going to cancel each other out. So when you add them together, you've got 0.4 going down, 0.1 going up, which means therefore the total current is 0.3 going down. So basically 0.4 minus 0.1 equals 0.3. So you have to remember to take the direction of the components into account when you're doing superposition theorem. Otherwise you will get incorrect answers. Okay, and again you can check this using multisim or mesh analysis, or after you've watched the whole video, nodal analysis as well. There's nothing to stop the aerospace students from looking at the nodal analysis video as well as the mesh analysis videos. It won't be on your exam, but it will provide you some extra skills that give you formative skills that you can take into your second year. Okay, so while it's not compulsory, I'm leaving all this information available to you so you can still watch it. Okay, so here's exercise 1. Have a look at that and see if you can get an answer for what the voltage here is at point V. Okay, so now we've done an analysis with a voltage source. So now let's do it using a current source. Okay, so here we have a circuit. So we have a current source here, these two resistors with a point V and V1 and R3. I would recommend you look at the exercise solution before you do this, because this is using this circuit where I've done source conversion on the V1. And as you remember, when you do source conversion, the resistance value stays the same, and use Ohm's law to then find the magnitude of a current source. So as you can see there, the resistance has gone from being in series to being in parallel. And I used Ohm's law, which is represented here, to give me the 0.333. So as I said earlier, the rule when you're using current sources with superposition is the open circuit them. So you've essentially just grabbed the component and you've ripped it out of the circuit. So that's what we've done here. So we've got a big gap here, and then you've got, essentially you can block out anything to the left-hand side of R1, because obviously no current is going to flow here. So the current circuit is the same as before, so the contribution, so V1 is equal to 1.11. And that is the solution that you did before from the exercise. So I'm not going to tell you that now. I'll go through that in the actual face-to-face session. When you have a current source, however, you can see here that the current would flow around here, and you've got R1, R2, and R3 in parallel branches. Okay, so we know that if we find the voltage is going to be the same across R1, R2, and R3, as we learned from the previous sessions. So we can combine R1, R2, and R3 all in parallel. So you can use your 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over R equivalent equation that we learned in the topic number 2. And you can then multiply that by the value of this source here, which gives you 1.11. So we know what the voltage from the current source is, which is 1.11 as well, as the voltage source, which is 1.11. So we can add those together. So 1.11 plus 1.11 gives you 2.22. And that is the answer here. So it's a simple case of just looking at the circuit and using the topic 2 basic circuit analysis techniques. Okay, it's as easy as that. Superposition theorem is probably the easiest of the 3 advanced circuit analysis techniques. Okay, so if by default you get a choice of using whichever, I always think superposition theorem is the easiest, but you might have your own different ones that you like and don't like. Okay, so we've looked at voltage sources, we've looked at current sources. So how do we deal with dependent sources. So remember, we covered these in topic 4, and that's why we did topic 4 before we did this, to introduce you to the concept of a dependent voltage source. Okay, so the rule with them is that they can't be removed from the circuit because they're dependent, as the name implies, on the voltage or current at another part in the circuit. So no matter what happens in superposition theorem, they have to be left behind. Okay, that's why this is highlighted under the theory tab. Okay, there's some more examples of using dependent sources in the tutorials, which we'll go through them. But now, let's move on to Thevenin's theorem. Okay, now Thevenin's theorem is where you can have two completely different circuits, and if they were in a box and you had two output terminals and you connected a measuring device such as an ohmmeter or ammeter or voltmeter to it, then you wouldn't be able to determine whether it was one circuit or the other because the outputs would be the same, like these examples here at the bottom. So this circuit here on the left is equal to the circuit on the right, and that's the whole point about it. And you might be thinking, why do I need to do this? And the purpose will be clear when we start doing topics 6 and 7, because in order to find things like the RC time constant, which lets you determine how fast a capacitor can charge up, you need to have one voltage supply and one resistor in order to do that. Okay, so if you have a large complicated circuit that's connected to a capacitor circuit and you want to find the charging time of that, then you can use the Thevenin's theorem to then reduce that all down, so if you've got just one voltage supply and one resistor. So basically, as far as the load's concerned, it could be any circuit that you wanted. So you can, if you get bored, you can create a variety of circuits. You can try building them yourselves. You can try simulating them in multisim, so you can have a go at this. So this is a circuit where I just said you've got an R1, R2, R3, R4, R5, R6, and you could then turn that into just one supply, what could be called the thevenin or VTH, and a resistance R thevenin RTH. Okay, so you can convert it from one form into the other. Just so you know what the quote says. So this basically says that any two-terminal linear is the key word here, can be replaced by an ideal voltage source V thevenin in series with resistance R thevenin, as such that a load circuit connected to it, for example a load resistor RL, is not affected by the substitution. So it sees exactly the same thing. Remember, I'm not going to ask you to write quotes in the exam. This is just so you know where it comes from, and it came from any of the textbooks. So it could be from a textbook that looks like this, for example. Okay, so how do you find these R thevenin and R thevenin? V thevenin and R thevenin. How do you find them? Okay, so the voltage is equal to the open circuit voltage across the two terminals when the second circuit's been removed. So you want to find the open terminal voltage across that. And the R thevenin is the resistance across the terminals when all independent voltage sources have been removed. Okay, dependent sources stay, independent sources remove, and we remove them in the same way that we did using superposition theorem. So a voltage source becomes an open circuit, and a current source, a voltage source becomes a short circuit, and a current source becomes an open circuit. So you effectively replace the voltage source with a piece of wire, and with the current source you rip it out, make a hole in the circuit, so it's an open circuit. Remember the difference between an open and a short circuit, because as I said in question 1 of the exam, and for other things as well, like the superposition theorem, you need to know the difference between them. And it's amazing how many students actually forget about this when it comes to the exam. So please, please, please remember. So a voltage source is replaced by a short circuit, which is a piece of wire, and a current source is replaced by an open circuit, which is a gap. So you've ripped the circuit component out. Okay. Okay, so now let's have a look at how we can calculate the thevenin for this particular circuit here. Okay, so with the circuit, we've got this 48 volt supply here. We've got an R1, which is equal to 12 ohms, with an R2 here in parallel across the voltage supply, or across the shunt across it. And then you've got the thevenin across here and the load here. So we've taken the load out, like we've said, and we want to find the voltage across here. So it's essentially a potential divider circuit, because you can see here you've got your 48 volts, there's your R1, there's your R2, so that's like your V out in your potential divider. So in this case it's R2 over R1 plus R2 times 48, or V1. So remember, R2 over R1 plus R2 times V1. That's your potential divider equation. So in this case, when you plug the numbers in, you've got 48 times 4 over 4 plus 12, which gives you 12 volts. Calculation of the thevenin, so you can see we had a voltage supply. So if we've replaced that with a short circuit, so in this particular situation here, you've got R1 in parallel with R2. So R1 in parallel with R2, so that gives you 3 ohms. So remember, I've removed the load, removed the sources, and then found the voltage across those terminals there. So let's imagine I've got a multimeter and I'm just measuring the resistance of that. Okay. So example, here's an example of a current source. So again, it's a slightly different circuit, so I'm just showing you that it's a different circuit, so it's not the same one, so you shouldn't get the same answer. So calculation of the thevenin. Okay, so we still want to find the open terminal voltage here, but since there's nothing here, the current's just going to flow around and around like that. So all the 5 amps is going to flow through the 3K, so you can just use Ohm's law. So V equals IR, so 3K multiplied by 5 milliamps gives you 15 volts. So that's our thevenin voltage for this one. And then for our thevenin, obviously we've removed the source, we've got an open circuit now. So if we've removed that, and as you can see here, the R1 is now no longer connected because you've got this gap. So the resistance is just 3K. Okay, so it's just a case of looking at the circuit and applying the rules. It's nothing complicated about it. Okay, if you follow these steps, you'll have no worries. And we're going to go through more examples in the tutorials. Okay, so we've talked about thevenin equivalent circuits. Now we're looking at a Norton equivalent circuit. So the only difference is that the thevenin looks at being a voltage source, whereas Norton looks at a current source instead. So what you could do is you could take your circuit, you could then use Thevenin's theorem to find a thevenin equivalent circuit, and use source conversion to then convert that into a Norton equivalent circuit. So that's one way of doing it, but there is a direct route that you can do as well. Okay, so basically that's just what I've summed up there. Okay, so Norton's theorem states that any 2-terminal circuit can be replaced by an ideal current source IN in parallel with a resistor RN, and that replacement is equivalent if IN is chosen to be equal to the current flowing through the terminals when it's short-circuited, and R Norton is the resistance between the terminals when all independent sources are removed. So finding R Norton is exactly the same as finding R thevenin. The only difference between the Norton and the thevenin source is with the thevenin source you're looking for the open circuit voltage, whereas in Norton you're looking for the short circuit current. So one is an open circuit and one is a short circuit. So again, it's like parallels with each other, the opposites of each other. Okay, so just remember that. Okay, so here's exercise 2. So see if you can have a go at that and see if you can tell me what the Norton equivalent circuit of that is. Okay, we'll go through the answers in the lecture. Okay, so now we're on the last aspect of today's video, nodal analysis. So please, aerospace students, don't turn it off just because you've got to this part. It still will be useful for you to know. Electrical students, definitely don't turn off because this will be on your exam. So Nodal analysis is essentially an electrical circuit analysis method of determining a voltage judging on the potential difference between 2 points or 2 nodes in the circuit, hence the term nodal analysis. And it relies on being able to apply Kirchhoff's current law to write an equation at each node. So it's like mesh analysis. So remember how in mesh analysis you're looking at the loops and you're using Kirchhoff's voltage law to find the voltage drops, to find the other drops in a loop, and the voltage supplied by the loop. So that was all using the voltage law. So nodal analysis is just using the current law instead. So let's get on with it. Okay, this is important to know. So this is like the equivalent of the 5 steps of mesh analysis that we did in topic number 3. So here we want to note all the nodes and junctions in a circuit with 3 or more branches connected. Okay, one's obviously with 2 components, the current and everything just stays the same, and if the current just goes through. Select one node to be the reference node. So that is usually the ground. Okay, so and you label that over 0 volt point. So I always label that as 0.0. Okay, you assign a variable for each node whose voltage you don't know. So you could call it Vx, Va, Vb, whatever. You then apply Kirchhoff's current law at each node. So basically you find out what currents go in, what currents come out. So you can find out what goes in, what comes out. Then you can sub in all your each unknown current into the equation using Ohm's law. You can find the voltage drops and things like that. And then like with mesh analysis, you can solve it using simultaneous equations. So this is why simultaneous equations are very important on this module. Okay, so if you've not had a chance to look at how to do it or look at it from a maths book perspective yet, then please do so because you need simultaneous equations for both mesh and nodal analysis. Okay, so here's an example. So let's consider this circuit here. So we picked a nice general circuit. So we've got 2 resistors, an R1 and an R2 here and here. You've got a voltage with a supply of 25 volts and you've got a current source on the other side of magnitude 100 milliamps. Okay, so that's our circuit. Again, you could solve this using mesh analysis because remember, you wouldn't be able to have a loop here, so you'd only end up having one loop. So this would be a relatively simple circuit to solve using mesh analysis. And of course, you could do it using superposition theorem. So find the magnitude of the V voltage, and obviously that would be an open circuit then. So again, you just have this one loop here, and then you'd have a short circuit here. So the current could come around here, and you could use current division on that. So we could do it with the 2 other techniques as well, and you can do this to double check it in your own time if you want to. So, step 1, we note all our nodes in the circuit where 3 or more branches are connected. So, obviously this node here is where V and R1 meet, so we don't need to note that. That one there is an unknown because that goes straight into there. So the 2 nodes we're looking at are basically this one here where R1, R2 and I meet, and this one down here where V, R2 and I meet, and the ground meets as well. So I'm going to call this one here our reference node. Okay. In regards to current, I know what the current from I is, so I will just leave that as I. I'm going to say I've got an I1 coming from R1, and I've got an I2 going through R2. So in this case, I don't know what I1 and I2 is. Okay, as I said before, I've listed that as the reference node, so I'm not going to go through that because I've already mentioned this. Label each node where I don't know the variable value, so the only thing I don't know is here, because that is Vx, so I don't know the voltage there. Okay. Then for each node, write the Kirchhoff's current law. So at Vx, you've got I plus I1 plus I going in and I2 coming out. So you have I1 plus I equals I2. So essentially that. You could write it in the other form of I1 plus I minus I2 equals 0, but I prefer the one where you've got everything going in on one side of the equal sign and everything coming out on the other side of the equal sign as well. So yeah, so there's my circuit. Now we want to substitute each unknown current using Ohm's law. Okay, so we know that Ohm's law is V equals IR, so I is V over R. So the voltage drop across each node is where you've got the high potential minus the lower potential divided by the resistor value. I'm sorry about that little pop-up going up then my email settings are out of date, so I apologize for that. So you've got this here equation here. So this all links back to what we were talking about in topic 1, about how the voltage drop direction is opposite to the direction of current flow. So remember that back from topic number 1 that we did. So we can put each of these at a higher potential and lower potential. So we know that this is the positive terminal of the battery, which means this side of I1 is positive, this side is negative. Because that's the ground, we know this is going to be the negative end, and that's going to be the positive end. And current flows from a higher potential to a lower potential. So from that point of view, our current flow directions are correct. So again, for our notion, I've basically said this, but we can start writing our nodal equation. So we know that we've got I1 plus I minus I2 equal to 0. So now we can start putting that in terms of voltages, because everything we know here is in terms of voltages. So we know what the voltage V is, that's 25. So we know at this side of R1, that's going to be at 25 volts as well, because these two are connected. This negative value here, this negative side of R1 and positive side of R2, and this here will all be at the same voltage because it's connected to point Vx. And we know here that that's going to be 0 volts there. Okay, and we know what I is. So we can start populating our equations, which is what this slide here says. So if you take a look, so I've got my I1 plus I minus I2 equals to 0. So I've just substituted in for each one of those terms in terms of Ohm's law, so the V over R component, because I is V over R. So the voltage drop across R1, we have V minus Vx divided by R1. So we have V on one side, we have a resistor, and then we have the unknown value Vx on the other side. So there's a drop of V minus Vx across that resistor. And obviously to find the current, we would then divide by the value of the resistor, which we know. So for that R1, we know what V is, we know what R1 is, we just don't know what Vx is. So that's our unknown value here. So we can substitute this value in here. We know what I is, and then we just do the same thing to find the voltage drop across R2. So we know there's Vx on this side, we've got 0 that side, so it's Vx minus 0 divided by R2. So our nodal analysis equation for the point Vx is V minus Vx divided by R1 plus I minus Vx minus 0 over R2 is equal to 0. So just look at each of the voltage drops across R1 and R2 and then sub everything in. So as I've said here, I've drawn each of the different bits and then I just sub them all into the equation. So just as a quick recap, so here is the positive end, here's the negative end, because this point is at the high potential, so that's connected to that. This is at 0 volts, so that's 0. Then you've got a plus there, and here's our unknown point Vx. So we know that V is on this side, we know this unknown value Vx on this side, so it's V minus Vx for the voltage drop across R1, and to find the current through it, we would divide by the value of R1, so it's V minus Vx over R1, and for R2, we have this unknown value here, we have 0 volts here, so the voltage drop across that is Vx minus 0, and obviously to find the current through it, we would divide that by R2, which gives us Vx minus 0 over R2, and then because we know I, that value we already know, and we can just sub all that into our I1 plus I minus I2 equals 0. I understand this might be complicated, and people might be going like, oh my god, I can't do this. It's just the same as mesh analysis. Just with mesh analysis, you're using the voltage law and putting things in terms of currents like I1, I2. Here, you're using the current law and you're putting things in terms of voltage drops instead of currents. So it's the same process, essentially, you're just using the other law, okay? So don't panic. And if you want to talk or discuss through this, find me after the lecture, put a hot question on and I can go through it again, or come and find me in my feature session if you don't want to ask a question in front of the class, okay? There's always help available, remember. Don't go, I can't do this. You can do this, okay? Have faith. Okay. And then there's your step 6, which is you're solving the simultaneous equations for each unknown node. So essentially you've only got one situation here. So you get your v minus vx over r1 plus I minus vx minus 0 over r2. So obviously you can expand these out. So you have v over r1 minus vx over r1 plus I minus vx over r2 equals 0. You would also have a 0 over r2 term, but because there's 0 on the numerator, there's no point in doing it because it's going to be 0 anyway. So that's there. You can then substitute all your values in. So you can see here the only two unknowns that you've got are the x. So because the only unknown you've got is the x, you can then rearrange that. Wait, first of all, you can do some of the maths here to put everything in decimal format. So then you end up with this. Then you can collect all your like terms, so collect all your vx's on one side, collect all your number values on the other side, then rearrange and solve for vx. So vx is equal to 0.35 divided by 0.03, which gives you 11.667 volts. So that node value vx is 11.667 volts. So now you know that, you can find all the voltage drops, which means you can find all the currents, so then you can find the power consumed and power supplied. So again, just know, well, in this case, you didn't even have to do simultaneous equations for it, but if you have two unknown nodes, then yes, you would. Again, like with mesh analysis, you would only get two unknown nodes in an exam. You wouldn't get asked for free. Okay, it's useful to know them for free, but I'm not going to be horrible and put 3 unknown circuits on an exam and having you to solve it using Gauss-Jordan. And besides, you'll be learning Gauss-Jordan in your engineering mathematics module. So that will be assessed in that exam. So I'm not really wanting to reassess the same learning outcomes that you do in different modules. Okay, so for example, if you wanted to find then I1, then you v minus vx divided by r1. So it's 25 minus 11.667. divided by 100, so then the current there is 0.133 amps or 133 milliamps. So that would then give you the value for the current in I1. Just to show you that that is giving you the correct value, there is a multi-sim simulation. So as you can see here, the current is correct, so it's 133 milliamps, as I just said, and here you have 11.7 volts. So my nodal analysis matches my multisim. And if you did it using mesh analysis and superposition theorem, you would get the same answer as well. So have a go at that. See if you can do it using all 3 circuit analysis techniques. Okay, here's a second example. And this one's a little bit more complicated because you've got a more complicated circuit and you're going to end up with 2 unknown values. Okay, so it's a bit more complicated, but don't panic. You can do this. Okay, so we go for exactly the same set of steps, okay, as we did in the previous example. Like I said, the only difference here is you've got 2 nodes to consider instead of 1. So again, I'm going to put my ground as my reference node at 0 volts. I've got my VA here, which is this node here where R1, R2 and R3 meet, and a VB here where R3, R4 and R5 meet. So, and I want to find VA and VB. Okay? So essentially that's done step 1, 2 and 3 all in one go. Step 4 is now where I add my currents to it. Okay? So I want to add the direction of current flow. So I'm going to take a bit more time and talk you through this slide in a bit more detail. Okay, so same process as before. So we first of all consider our voltage. supply V1, so say the current coming out of that is I1. And this is a positive terminal, so the current's going to flow in this direction. Current's going to split at VA, so it's going to come along and it's going to split. So you've got I2 going down, say, and I3 going across, like that. So then you've got I3 going into VB. Now note V2 is pointing downwards. So that's your positive terminal. So the current's going to point downwards, so it's logical that the current's going to flow in this direction. So it's going to flow down, and then you've got R5 that comes out as well. So we can say that at VA, or node A, then you've got I1 going in, and I2 and I3 coming out. So I1 is equal to I2 plus I3. So here, you've got I1 going in, and you've got I2 and I3 both coming out. For node B, or VB, you've got I3 going in, so through here, and you've got I4 and I5 coming out. So it's just like with mesh analysis where we're looking at allocating our currents. So now we've got our currents, let's look at the polarity of the voltage drops now. So let's start with V1 again. So that's your positive terminal of your battery there, which means this here is going to be your positive end of the resistor. So that's going to be your negative end. Because this is a ground, this is going to be the negative end of R2. So that has to be the positive end. And again, like this one here, that's going to be positive, because your current flows from your positive to your negative. So that's going to be your positive end, and that's going to be your negative end. Looking at supply V2, this is your negative end here, so which means that's going to be your negative end of R4, and that's going to be the positive end of R4. Then, because the current's flowing again around here, then current flows from high to low potential, so this must be the positive end, and this must also be the negative end, because it's also connected to the reference point or the ground plane of 0 volts as well. So just go through your circuit and look at how you allocate the polarity based upon the voltage values for the ones you know and the current flow directions as well. Okay. Okay, don't panic about this. Okay, this is just, the maths is a little bit more complicated because you've got more unknowns. But don't worry, I'm going to talk you through this. So for point VA, we had I1 minus I2 minus I3 equal to 0. So our I1 is the current through R1. So we know we have V1 here at minus VA. So V1 minus VA will be the voltage drop across R1. And to find the current, we would divide by R1, which gives us 25, which gives us this value here. Okay? For, wrong direction. For R2, you've got your VA here, you've got 0 here, so it'll be VA minus 0, which will give you the voltage drop across R2, and you would divide that by the value of R2 to find the current, I2. So VA minus 0 divided by R2 would give you the current I2. And then the last one is the current in R3. This is where you have both unknowns. So you'd have VA minus VB. So you'd have this potential drop here. And then you divide that by the value of R3 to find the current. So VA minus VB divided by R3. You could then obviously expand out each of those division signs to end up with V1 minus V1 divided by R1 minus VA over R1 minus VA over R2 minus VA over R3 plus VB over R3. And you're probably wondering, why is that a plus? Because you've got a minus sign here and a minus sign here. So the two negatives will make a plus. Once you've got that, you can substitute your numbers in, collect all your like terms, and get an equation in terms of VA and VB. So when you've collected all your like terms, you should end up with minus 0.165 VA plus 0.025 VB equals to minus 3.2. So that gives you your first nodal equation. If we move on to our second one now, then you've got this here. So you've already got your I3 component here, which is your VA minus VB over R3. So that's the current going in. And then you need to find I4 and I5. So here, for R4, you've got VB minus V2. And that minus V2 is due to the polarity of the source. So remember, it's pointing downwards. Okay? So that's why that's a negative, because it's pointing downwards. Okay? So potentially stuff's flowing away from it, which is why it's negative. Okay? And then for the R5, it would be VB minus 0 divided by R5, because you've got VB here, which will be your positive end. You've got 0, which is your negative end. So VB minus 0 over R5 would give you I5, which is here. Like before, you can expand out all the division signs. You can then substitute your numbers in, simplify the maths, collect your like terms, and you can get your second nodal equation, which in this case is 0.025 VA minus 0.095 VB is equal to 1.5. And now you've got your two simultaneous equations. So now you've got your two simultaneous equations, like so. You can solve those to find what the value for VA and VB are. I'll let you do that in your own time. Remember, you can also use MATLAB or Wolfram Alpha to check your mathematics, but you should end up with VA of 17.706 volts and VB equal to minus 11.130 volts. Okay, and finally, you want to find the desired current through R3. So I3 is VA minus VB over R3. So you know it's 17.706 minus 11.130 divided by 40, which gives us 0.721 amps. Now you're probably wondering why this is a negative value. And again, that is affiliated to the fact that this supply here is reversed. So that's pointing the other way. So this value here is going to be of the negative side because it's connected to the negative terminal of the battery. And this side is going to be the positive side. So that's why VB has a negative value for it. So remember, you can just do basic checks by just looking at the circuit. And if things don't look right, then you can probably know in a few seconds that if your math has been correct or not. In addition to using Wolfram Alpha or MATLAB to check your calculations, you can use multisim as well. So here we've checked for 2 points. So here we've got 17.7 volts and minus 11.1 volts, which matches obviously the values we got here and here. And again, we've plugged an ammeter probe in here to give us 721 milliamps for the current through R3. So that's just proving that the maths is correct. If I go back to the main circuit, so if I go back to that circuit again, you've got two current sources, so you could do mesh analysis on this. The only trouble with mesh analysis for this is you would end up with 3 unknowns. So you would have one loop here, and one loop here. So from a circuit analysis perspective here, using nodal analysis, because it only gives you 2 simultaneous equations, makes it a mathematically simpler solution to do. So sometimes when you're considering mesh or nodal analysis, look at how many unknowns it will give you and then choose the one with the least amount of unknowns, because that will make the maths easier, which also reduces the chance of any mathematical errors being introduced in your calculations. Okay? And again, with superposition theorem, you would just look at the contribution by V1 and by V2 separately, and then you can do your analysis based on that. And again, you can simplify the circuit using the techniques from topic number 2. So yeah, have a go, see if you can get the same answers. There are some examples on Moodle when I've done a circuit with all 3 circuit analysis techniques, so you can have a look at that as well. Here's an exercise 3 now. So here is one where we're using nodal analysis to find the current through resistor R2 and the voltage cross resistor R1. And again, you can verify it using superposition or mesh analysis. So this is a circuit, and I've deliberately put one in here where you've got a voltage source and a current source. Okay, so you can test your mathematics with both of them. Okay, so let's do our steps like we did before. And there's an exercise 4 that I'll go through as well. So have a go at that, which has one of each, and have a go at that as well, which has 2 of power sources and 1 current source. So I'll go through those in the lecture session. But have a go at them beforehand. See if you can get an answer. Again, you can check it using superposition, mesh, multisim. So yeah. Okay, so that's it for topic number 5. I hope you found that interesting, and hopefully you'll join me again for another 102 CD video, and what struck 102 CM video next time, because that would be covering topic number 6, where we start introducing you to these things here, which are capacitors. So yeah, so we're going to start having a look at these things next week, or next time, I should say. Okay, so yeah, take care, guys. Don't work too hard, and I will see you soon. Bye-bye.